You said it.
No, you left your thing.
What? Soul.
It's not mine.
I think the 3. I think 3 is good.
Or like didn't properly measure.
So Zach, thank you for rounding.
Oh,
You guys mark your pen?
No.
yeah, I measured it.
Could somebody towards the back of the room do me a huge favor? Arrange the carbon paperback neatly into that file folder.
I got it.
Thanks. Oh, I'm sorry, what?
What did you guys get on your error?
I kept that stuff protected for this lab and also
Ryan, why are you talking
on the second semester.
so
1.5.8.
And I just use it
That's
over.
not what I sound like.
It's hard to find it.
How no, went on eBay.
I'm sure I
Okay,
could.
I've never taken it, but ever sound like
I
that.
probably sell some version of it. But that stuff is really dark. So it's really
In your head, I sound like it.
Is there a certain number for the error percentage that doesn't count?
As you'll discover, because there's lots of things that can go wrong in these lab exercises, this is usually not a very accurate means of measurement.
Okay, that's good.
There are much more accurate ways of doing so. We'll look at some of those later.
They
Oh,
got
they got
5%.
26. They got
We
26.
got 38.
It's hard to measure change this way. I'll go through the errors in a couple of
Oh, I
minutes.
just did 0.04.
I'm making sure that all of the groups will have a chance to get all of them.
You're walking right? Sure.
So, yeah, if you can do me a huge favor, bring Stan.
Which quality is the source of error are
And then cut away with washer. Where were the rulers? Rulers come up here, and also rulers.
So are we writing that? Is that what we're writing on number 4?
Basically, yeah. You may not want to say it.
They will wrap up and go over the errors briefly in about 5 minutes or so.
Oh yeah. Our angle.
I just know that he didn't sign up.
What's it called? Bubble buddy?
It's hard to measure. It's not a figure. Well, they've been in this class forever since I started working for them 20 years ago.
I don't know.
Just turn it around so it's like facing that way.
But,
Measurements for.
all right, girls, let's do it. Why not regular states?
We can get it where? Did she like what she did nothing else?
Oh, Griffin.
They don't care about
Why
anything.
are you?
Really?
Yeah.
So even
Hey,
your
that's-
background.
that's hard. Stop.
Okay.
God, I'm so comfortable. Okay.
Yeah, but I have a
I'll
little
even
bit
like
of
this.
higher
Are you a Yeah.
I would be.
You have really like mine.
My mind's too big.
Good enough for, should be good enough for top off.
It better be good. Oh God, a margin in there.
Smart. Wait,
Is it
early, like 7 minutes early.
in the engineering school?
Oh, our teams are next to
Yeah,
us.
she's like, we get out 7 minutes early.
But architectures are in love with administering now. Yeah, I think
Because
that's
you were doing, I was doing your face, you were like, Ryan, you were like 11.
You mean, oh yeah?
Yeah.
Yes, thank you.
No, I think the average for like Pepperdine.
This is yours.
Thank you.
Henry.
Oh.
Shirley, this is yours.
What is this?
Griffin, this is yours. Shirley, do me a favor, put these on the tape.
What is that?
I feel like getting it. Yes.
How did I get a 10?
Okay, I
Wait, I got a 10.
All right, everybody start moving back to your seats, please. If you haven't cleaned up something at this point, please do so. Let's briefly wrap up this lab exercise by going over the errors, and then we're going to finish up projectiles today with a couple of problems in the period. Yes, Henry?
are we turning our lab thing?
I will collect them from you at the beginning of the period next time. That's fine, even though it looks like most of you are just about done. Okay, with regards to the errors, as a lot of you discovered, this is not really the best way of measuring G. It's hard to get an accurate result here because lots of things can go wrong. Number one, and you have no control over this, but we're assuming that the initial angle here is equal to 0 degrees. Some of you may have noticed that some of these ring stands and the rings themselves, the clamps are a little bit bent in some cases. So we're assuming that theta naught is equal to 0 degrees. In some cases, it may not be exactly equal to that. Okay, then secondly, usually the biggest source of error here in this lab exercise is the uncertainty that comes in finding the origin. This then leads to erroneous measurements for both x and y naught. As we say, that error propagates. It leads to incorrect measurements for x and y naught. Okay, and then third, just measuring error all by itself, especially when y naught is a large value, if you have to use 2 meter sticks or multiple rulers or something like that to measure a large value of y naught, there is definitely an error associated with that. So I won't be surprised if you end up with a poor result. The more careful you are, the better the result should be. But yes, lots of things can go wrong. Henry?
Was there any definitive way that G was measured, like for certainty?
The monkey hunter demonstration is an example of how you can show that G is exactly 9.8 meters per second squared for a projectile, as opposed to something that's being dropped horizontally. I think that it was originally measured in the first simple experiments that were done in the late 17th century, by like dropping an object from rest at the same time that you launch a projectile horizontally. It was basically done like that originally. But as you discovered today, this is not the most accurate means of measuring G, the best way that is. All right, put this aside, please, and take out your notes if they're not already out. We're going to be finishing up projectiles today with a couple of examples. Once we've done those examples, then we've kind of really exhausted all possibilities associated with this projectile motion. Okay, let's begin with an interesting little proof. And that's the following. It's right here on the screen. Prove that a projectile's range is maximized, that is the biggest number that it could possibly be, as long as the projection angle is 45 degrees. Now, if I asked everybody here in this room, at what angle should you throw a projectile to ensure that horizontally its range is as big as it's going to be, probably 99% of you would immediately say 45 degrees, which is intuitively obvious. However, we have to prove that here specifically and mathematically. If I throw a projectile at a 45-degree angle, I'm going to ensure that the range here, that horizontal displacement, when it returns to its original height, is as large as it can possibly be. That's what the question is asking us to prove. Okay, now this is a range situation, and remember what range situations look like from last time in class. Okay, for simplicity, we're just going to launch here from the origin. So both x naught and y naught are 0. And then right here, in component form like so, is the initial velocity v naught. Okay, as we'll see, the initial speed itself doesn't matter. Okay, right here is the angle theta naught like so. Now for a ranged situation, the object travels its entire parabola, so it returns to a vertical position of 0, and then right here horizontally is the range x. So in terms of this diagram and in terms of these variables, an alternate way of stating the problem is simply to prove that x is maximized when theta naught equals 45 degrees. So that's basically what the problem is asking us to do. Okay, now we begin with our two-position equations. For this particular example, we won't need the velocity equations, but let's just take a look at our two-position equations. First of all, vertically, before I simplify it, we have the following. And And then horizontally, once again, before I simplify it, we have the following. Okay, just before I begin the algebra here, what I basically need to do is find an equation for x, the range, that's specifically just in terms of the angle theta naught. That's what I'm going to be looking for here algebraically. Finding this expression, as you'll see, is actually pretty easy to do. The way that I begin this process is to plug in my zeros first. So in the vertical position equation for a range situation, remember that both y and y naught are equal to 0. So I'll plug in those zeros there and start to simplify the vertical expression like so. And then before I go any further at all in the problem, I can actually go one step here further algebraically. Notice that because this is 0 here on the left-hand side, I can safely cancel out a t here from each term. So, okay, and then next, right here, I have my horizontal position equation. In this expression, only one thing is equal to 0, and that's x naught. So we just simplify that like so. And then once again, what I want to come up with is an equation that describes x in terms of the angle. This means that from this set of expressions here, I need to get rid of the time t. So I'm going to algebraically combine the expressions together by taking the bottom expression and solving for t, and then I'll plug it into the top expression right here. So doing so, solving for t in that second equation, just divide by v naught cosine theta naught on both sides to give me the following for the time. And then take that expression for t and plug it into the equation above. So doing so carefully, we'll have 0 is equal to v naught sine theta naught, and then minus 1/2 g times t, this quantity right here. And then if I just solve this expression for x, I'll then have what I'm looking for. I'm looking for an equation for x in terms of the angle theta. So at this point, it's just a couple more brief steps. Let's take this term here and move it to the left-hand side first. I'll kind of rewrite it slightly as I do. Like so. And then to solve for x here, just cross-multiply all the other stuff to the other side. So then as I do that process, I get to here. So I'm just moving all the stuff over to the other side. So, and then when you get to this step right here, you say to yourself, okay, well, what do we do next? It looks like we're kind of stuck. However, if you look at this expression carefully, do you see a trig identity? Which one is it?
Sine 2 theta.
That's right, sine 2 theta. It's one of the double angle formulas. Now, if you're having trouble seeing that, let me just kind of rewrite this expression here in the following way. Let me group the trig terms and the 2 here in parentheses. Like so, yeah, that's one of the double angle formulas. Who would have thought that there's a trig identity contained in this description? And there is. This trig identity right here, and don't worry, I'm not going to ask you to prove it or anything like that. But this trig identity that's right here is this one here. It's one of the double angle formulas. It's sine 2 theta. You then end up with the following equation. This equation, by the way, is given a name. It's called the range equation. I'm using this problem as just a means of deriving it for us here in class. But the range equation, as it's called, is the following. So I've derived it here in class in the context of this example, and now I'm going to apply it in this example, and then in a little while, another follow-up example that's a nice sequel, if you will, to this problem here. Now we'll apply it for this specific problem. Okay, let me erase this algebra. I don't need any of this junk anymore. So now how do I apply the range equation? Let me just rewrite it here for this following example. Well, these coefficients right here don't matter. What does matter, however, is that for some specific value of V naught, whatever it happens to be, x will be maximized its greatest possible number when this trig term right here is its biggest possible number. What is the biggest possible number that the sine of an angle can be? many is it?
One.
Yeah, it's 1. So in other words, x is maximized when sine of 2 theta naught is equal to 1, regardless of what the v naught is. For some specific value of v naught, x will be as big as it can possibly be, when this term here is as big as it can possibly be. Now, what is the biggest number that the sine of an angle can be? It's 1. So then therefore, the sine of what is equal to 1? 90 degrees, not 45 degrees, but 90 degrees. Keep in mind that contained here, the angle is actually 2 theta. Sine of 90 is equal to 1. So 2 theta is 90 degrees. Now divide by 2. Theta naught is 45 degrees. So yes, if you launch a projectile at a 45-degree angle, its range is going to be maximized. The biggest possible number, this right here, proof. So I use this example as a means of deriving the range equation. Once you understand the derivation, you can just keep using the equation over and over as is appropriate in examples. So as a nice little follow-up to this particular problem, here's another example of the use of this equation. This one's kind of cute. I like this one too. Every now and then we do some cute problems. This one's kind of cute too. Because it's a people. Okay, now after you finish copying the problem, I'm going to get rid of some of this stuff here, but just reproduce this basic diagram because this is once again a range situation. So, okay, a bullet is fired at a target at the same height. So think of the bullet being launched from the origin and the target is at the same height, so it's once again a range situation. Okay, the range itself horizontally is 100 meters, and the bullet's initial speed is 380 meters per second. That's a realistic number. It's a little bit above the speed of sound. At what angle or angles should the gun be aimed in order to hit the target? Okay, now remember one of my examples from last time in class. What would happen if you aimed the gun horizontally? Exactly horizontally. Are you going to hit the target? No, because remember that the projectile is going to fall vertically downwards. That's what we did in the problem last time in class. So then therefore I am going to have to take the rifle, for example, and aim it at a slight angle like so. But notice how the problem is phrased. It says at what angle or angles. In other words, another possibility. Should the gun be aimed in order to hit the target? Now, how else could I possibly aim the gun to ensure that I hit the target, in this case, 100 meters away?
Almost straight up.
Yeah, take the rifle and aim almost straight up like so, such that when you fire the projectile, you'll hit the target. If you can, by the way, hit the target that way by aiming a gun, more power to you. But there should actually be two answers. Okay, now how do I visualize this? Well, it's once again just a range situation where we have the following numbers. V naught is 380 meters per second. The range itself is given in the problem as 100 meters. And now in the equation expression itself, the range equation right here, notice that the only unknown is the angle, so I can go ahead and solve for it. So I'm going to take the range equation, once again applies to this situation, and I'm going to solve it for the sine of 2 theta naught. So take these guys here and just move them to the other side. And I get that the sine of 2 theta naught is then therefore gx over v naught squared. Now let me just plug in my numbers there and let's just see what we get. So plugging in my junk appropriately, 9.8 times 100 in the numerator, divided by 380 squared in the denominator. And this comes out to be, out to a few decimal places, 0.0067. Okay, now just before I take the inverse sine here of both sides to begin to solve for my angle, think now in the case of your basic trigonometry. How many different angles have a positive sine? 2. In terms of the unit circle diagram, which two quadrants have a positive sine? First and second quadrant, now wait a second. All right, I can understand how if my target is over there, I have to fire the rifle into the first quadrant like so, and then hit the target. But how is it possible that I'm firing the rifle like so into the second quadrant and hitting the target? Well, watch carefully. What I'm going to do is just do inverse sine of both sides. And when I do this, I'm not solving for theta naught, I'm solving for 2 theta naught. So watch what happens as I do this. So first of all, the inverse sine of this thing right here, it's still here in my calculator, so inverse sine of that, and I come up with about 0.4 degrees. Now that's the first quadrant angle. It's not my answer though, it's 2 theta naught, not theta naught. But that right there is my first quadrant angle, and then its supplement would be the second quadrant angle, which would then therefore be what? It would be 180 minus this, which is 179.6 degrees, 179.6 degrees. But that right there is not the answer. The answer is to take these two numbers and divide them by 2. So then therefore, the first angle, theta naught now is 0.4 divided by 2, 0.2 degrees. That makes sense. You aim just above the horizontal to ensure that you hit the target. And then the other value here is 179.6 degrees divided by 2, which is actually 89.8 degrees, like so. So yeah, you very nearly aim the rifle straight up like so to ensure that you hit the target. And there's a second answer here that is a solution to the problem. Once again, a nice little cute example. Okay, and then lastly, I'll finish now projectiles, which is one more example. It's not quite the same thing as this, but it's a nice little proof problem as well. It is also quite cute.
What do you mean by cute?
Just because they're interesting problems. They're cute. They're cute problems.
No.
like them. Right?
All right, quiet down, please.
Mr. Shaw,
Yes, go ahead.
do you ever apply these skills in real life?
Do I ever apply these skills in real life? That's what I'm doing right now.
I mean, like, do you ever go out and like the shooting range?
Oh, do I ever go out and shoot rifles and so on and so forth? Yeah, once in a blue moon, but
Do you-
I mean, usually when you fire at a target, it's usually closer to you than say 100 meters. 100 meters is quite a big distance. 100 meters, by the way, is about from the back of the classroom there to the doorway, all the way out to like the middle of the park. That's a pretty good distance.
Yeah, that's all.
Those.
Okay, notice the problem here. It's once again a proof type of problem. It's not the same thing as what I just did here, these last two examples, but it is a similar situation. Guys in the back. At what angle, so it's looking for a number, must a projectile be launched from the origin such that the range is twice the maximum height? So what the problem is basically saying is this. So let's say I throw the object and I do so from the origin at a very specific angle. So it looks, say, something like this. What we want to calculate is exactly what angle do I have to throw it, such that the range here, x, is twice the maximum height. This will occur regardless of what the initial speed is. The only thing that is important is the angle that I throw the object, such that the range is twice the maximum height. That's what we're looking for. Now the key to solving this problem is to basically take what is said there in words and rewrite it as a mathematical expression. Here's how we'll go about doing that. First of all, we have a speed here, v naught, which we'll see is totally unimportant. And then right here is our unknown projection angle that we're looking for in the problem. Okay, we're launching from the origin once again, both x naught and y naught are 0. And then we're basically taking a look at 2 points here on the parabola. We're looking for, first of all, the midway point, if you will, like so. That's going to be our maximum height. But then also right here, we're looking for the range, the horizontal displacement for the entire parabola itself, like so. And now taking what is given there in words and rewriting it as a mathematical expression, you would have to think of it like this. Basically what the problem is asking us to do is find theta naught such that the range x is twice the maximum height. So notice how I've taken what is said there in words and I've written it as a mathematical expression. And then to begin my algebra, what I now want to do is just take my horizontal position equation x, where x naught is equal to 0, and set it equal to 2 times my vertical expression, like so, my vertical position equation, where once again, y naught is equal to 0. So now I just fill my basic expressions into this equation that's basically given. So first of all, have x for the range, where x naught is equal to 0 is equal to this. And that then equals 2 times the maximum height. Here's my vertical position equation, where y naught, remember, has been set equal to 0. So once again, here on the left is the range, and that equals then 2 times the maximum height, which is here on the right-hand side of the expression. Now, as I wrote down this equation, x equals 2y, I made a mistake. Something is not quite correct here. This is once again x, this is the range, and this right here is y on the diagram above. This is the maximum height. Something is not quite right. Ryan, can you tell me what it is?
For the range, you should have 2t
Because?
because the max height happens in the middle of the projectile motion, while the range is at the end.
He's exactly right. He spotted the difference here is that the times are incorrect. In other words, if I call the time from here to here for the maximum height, the right-hand side of the equation t, as I did, then on the left-hand side of the equation for the range, that time has to be twice as much. Very good. I have to correctly account for the times being different in this manner. That's excellent, Ryan. You did a good job in spotting that immediately. Okay, now what I want to do is take this expression and start to simplify it. Notice that the 2's actually cancel out, like so, as does a t from each term. Like so, now here's what's left over after I do that minor cancellation. And once again, what I'm trying to solve for here is the angle, theta naught. Notice that at this point I kind of run into a problem because I really can't go any further algebraically with this expression all by itself, trying to solve for theta naught. So I need to come up somehow with a new equation. That's easy to do. Here's how we go about doing that. Let's jump up to the top board for just a moment. Okay, right up here at this position, when the object is at its maximum height, if you remember from last time in class, in which direction is the velocity vector at that moment?
Horizontal.
It's horizontal, like so. So then therefore, what is the y component of that velocity vector equal to? It's equal to 0. Now remember our velocity in the y direction equation from last time in class. That's this expression here. Notice that if I set the left-hand side of the expression equal to 0, right here at this moment at our maximum height, I can then solve for the time t. Once I have that time t, I'll plug it into the equation on the bottom board. And the time t here, by the way, is t, because we called t from here to here, and this is what we're analyzing. Remember on the bottom board from here to here was 2t, so therefore from here to here is time t. I can now solve for it. So set this guy equal to 0, when we're right here at our position for the maximum height, like so. Move this quantity to the other side and divide by g. After you do those couple of minor mathematical steps, you end up with this expression here for the time t. And then to finish the problem now, I'll take that time t and plug it in right here. And now watch what happens. It's almost magical. But as everybody here is aware of in this class, there's no such thing as magic. So now watch what happens, folks. This is very cute. First of all, have here on the left like so. And now on the right-hand side, I'm going to have v naught sine theta naught minus 1/2 g times t from the top board, which is this. So, notice that a bunch of stuff simplifies. I first of all have here on the right-hand side, the g's canceling out like so. And if you also take a look carefully at each term, what else cancels from each term? V naught. So the initial speed is unimportant. It cancels from the expression. And now here's what's left. I have cosine of theta naught there on the left-hand side. And then on the right-hand side, it's sine of theta naught minus 1/2 sine of theta naught. So all that I have left are numbers and trig terms. So I should be able to solve for the angle. Now on the right-hand side, what is sine minus 1/2 sine? It's just 1/2 sine. So therefore, cosine of theta naught is now just 1/2 sine of theta naught, like so. And then the last couple of steps here is to merely do the following. Take the 2, move it up to the left-hand side like so. Take the cosine, move it down to the right-hand side like so. And now here on the right-hand side, I have sine over cosine, which is equal to what?
Tangent.
It's equal to tangent. So tangent of theta naught is equal to 2. The answer is going to be the inverse tangent of 2. So let's say it's the inverse tangent of 2. So inverse tangent of 2 is about 63.4 degrees. And that's the answer. So in other words, if you throw a projectile at a 63.4 degree angle, regardless of what the speed v naught is, the range, this distance here, is going to be twice the maximum height. That distance there, that's a nice little proof to examine here at the end of projectile motion. So with these last few examples that I've done here today, we've pretty much have exhausted all the possibilities about what we can say about the kinematics of a projectile. Okay, let's go ahead and take a look at the board. Okay, next time in class, on Wednesday of this week, I'm going to collect a mini lab at the beginning of the period. Don't forget about the double web assign this week as well. That's due on Friday, that's due on the 10th. And then lastly, if you remember, does anybody recall what is happening this Wednesday, right before dawn? Yeah, total lunar eclipse. Here's some information about it for you. No, you look at this one.
No, they're actually missing one. It's like my dad's side? No, it wasn't my dad's side. There's my dad's side. Well, they are.
All right, admittedly, the lunar eclipse kind of falls at a bad time of the morning. It's basically right before dawn. But here's what I suggest that you do if you want to get up early and see it. And I do encourage you to do so, especially if you've not seen one before. It should be very nice. It should be very spectacular. Okay, mid-eclipse, right in the middle of totality, is at 3:55 in the morning. And then it will still remain a total lunar eclipse for about an additional half an hour. And then the partial phase will begin going out the other side as the moon begins to emerge from the Earth's umbra. It'll go from being total to then increasingly less and less partial over the course of the next hour or so. It will then have emerged from the umbra here according to the chart that I provided for us. The partial eclipse ends at about 5:34 in the morning. So then, at that point, it's like, okay, the eclipse is over? Well, not quite, because the moon, even though it will be fully lit, it will look like full moon, is still going to be in the Earth's penumbra for about another half an hour or so at least. This is when the moon definitely takes on a three-dimensional appearance, even though it looks full in the sky. The reason for this is because when it's in the Earth's penumbra, the light that's striking it from the sun is striking it from the side somewhat. So even though the moon will be full, it won't look like a completely flat disk in the sky like it normally does during full moon. It will definitely have a noticeable three-dimensional appearance. Now for me personally, I usually get up at 4:45 in the morning anyway on any normal day. So I'm just basically going to get up about an hour earlier, so maybe around 3:30, and then essentially watch the second half of the eclipse right before I get ready for work. So I suggest that you do some version of that as well. I know that it falls in kind of a bad time of the day like this, being right in the middle of the morning, but it is going to be really nice. Okay? So I encourage you to take a look. Yeah, Henry?
You wake up at like 4:45 when you go to bed.
Usually around 10. I barely sleep. Okay, Sean, you have a question? Yes, this is Wednesday morning, so less than 48 hours from now. Okay, so prep for it, in other words, tomorrow night. Tuesday night, set your alarm early.
I'm a free second.
There you go.
All right.
Get up, look at it, and go back to sleep, right?
I thought we were going out there.